Hey, what's up everybody? I'd like to welcome you to another audio programmer tutorial. And in this video, we're going to create a simple sine wave oscillator to make our first sound plugin today using JUCE and C++. Here's a demo of the plugin we'll be making today. Now, I know that doesn't look like much, but if you're learning the fundamentals of audio, there is actually a lot of information that is going to be packed into this tutorial. First, we're going to discuss how to create an audio processing class. This is going to follow the same type of blueprint that you need to know about to create your own audio processing class or use DSP algorithms from other developers. Then we're going to shift gears to math, where I'll first show you the sine wave algorithm, then show you how to convert that math into code. Then we're going to take that code and implement it in our audio processing class. I'm going to show you two ways that you're going to be able to write this class. The first is going to be using JUCE tools, and then I'm going to show you another way that just uses standard C++ without any other dependencies. Now, if you're feeling intimidated, don't worry. I'm going to explain all the concepts along the way to help you get started. If you're curious on how to get started with building your own plugins, be sure to check out our community, resources, and services. You'll find all of these on our website, theaudioprogrammer.com. I'll also put a link of the code in the video description below. And without further delay, let's get started. Okay, so here we are in a fresh new project. And if you have any questions on how to get set up with a project, how to start a new project, or what these source files are, such as the differences between the plugin editor and the plugin processor, be sure to check out some of the earlier videos in this series. I have a CMake template that is pretty much what this is, and you can download that from our GitHub, and I explain all of those differences. In this video, I'm also using Sine with CMake, which is now free for community users. And if you're using the producer for JUCE or any other IDEs such as Xcode or Microsoft Visual Studio, the concepts are largely the same, so you can follow along with whatever IDE that you might be using or whatever setup that you're in, and you'll be just fine. The first thing that we're going to do is create our audio processing class. So we need some new source files, and the way I do this in Sine is by right-clicking on the source folder, to new, to C++ class. So I'm going to call this class sine wave. Now, if you're using CMake, you need to make sure that you add this to the CMake list as source files that you're going to build. Now that I've added the source files, I need to reinvoke CMake. You can do this natively within Sine itself just by going to the CMake menu in the top of the bottom left, and then hitting the sprocket, and then choosing Reset Cache and Reload Project. If you're using Xcode or Microsoft Visual Studio, then you need to reinvoke CMake in your command line. If you're using the producer, then you would do save and open an IDE from the producer. Now that that's finished, I'm going to go ahead over to my sine wave header file. I'm going to make public and private sections here. So now we're going to create some functions that are very typical for any type of audio processor or DSP algorithm that you're creating. And in this case, it's a sine wave, but it could be a delay or a distortion or a reverb. And what we need to do first is determine how often we need to do the calculation for the DSP algorithm, how many times per second. And this is determined by the sample rate. So many of you are familiar with DAWs such as Ableton or Reaper and know of this term called sample rate, and this refers how many calculations your computer is going to make for 1 second of audio. So typically this would be a value like 44,100 or 48,000. So this means that your audio processor would be calculating this DSP algorithm 44,100 or 48,000 times per second. And this is normally changed or modified within a setting within your DAW or by your sound card. So let's go ahead and create the prepare method. Now we need to create an implementation of prepare in our sinewave.cpp file. So one question you may be asking is why sample rate is a double. And the reason is simple. We're going to be creating the sine wave algorithm later on in this tutorial within our audio processor, where we have this method called prepare to play. This is the method that's called when our plugin is first instantiated or if the sample rate changes to make sure that we're passing in the correct sample rate. So the sample rate variable that we're getting from prepare to play will have our sample rate, and then we're going to pass it in to the sine wave algorithm here. So the only reason that I have this as a double is to correlate with the sample rate variable from prepare to play. And you'll see how this works a little bit later on in this tutorial. So while we're here in the plugin processor class, we're going to scroll down a little bit further to process block. So as I've mentioned in previous tutorials in this series, the process block is the main meat of any real-time audio application. So this is the place where all of the magic happens, where audio gets generated or it gets changed in some way and comes out of our speakers. And the way this is done is using this JUCE audio buffer object. So this is a space in memory that gets filled with our audio data. Then that audio data may get manipulated in some way, and then it comes out of our speakers. So what we're going to do is we're going to create a function called process that's going to be in our sine wave class, and we're going to pass in this JUCE audio buffer so that we can fill that buffer with our sine wave. Now what you'll currently notice is that the JUCE name is in red, which means that our object for this audio buffer is not being recognized. And you can see if I try to compile this plugin right now, we get this error, use of undeclared identifier JUCE. This is because we don't have any headers that we've included, any description of what the audio buffer class is or where it's coming from. So what we need to do is we will go to the JUCE documentation for audio buffer. And inside here, there's a little hint of which header that we need to include in order to get access to this audio buffer. So this is in a library called JUCE Audio Basics. So JUCE is actually a collection of libraries, and one of those libraries is the Audio Basics library. And now we should see that goes away. So now we're okay. And now we just need to create the process method implementation in our CPP file. So now let's go ahead and just compile this, make sure that this is running okay. All right, so our build has succeeded and we can go ahead and move forward to the next step. All right, we're going to take a temporary shift away from the exciting world of code into the exciting world of math. And if this type of equation looks a little bit daunting to you or intimidating, don't worry. I don't come from a traditional math background myself, and I'm going to go ahead and show you what each part of this equation does, and then show you how you convert it into code. So just stick with me and you'll be just fine. So one of the most confusing aspects that I had to wrap my head around when I was first looking at this equation was that I used to think that this sine wave equation would be performed once and this would give us back our entire sine wave all at once. And that's not the case. So you have this aspect t, which refers to time. And the way that this equation is represented shows us that what's happening is that this is converting one point in a series of points. Then later on, what we do is we connect those points, and that's what's going to give us our sine wave. So you may be asking yourself, well, how many times do you need to do this calculation to give us a sine wave? And that all goes back to sample rate. So as we know from earlier in our discussion, if we were talking about a sample rate of 48,000, that means we need to have 48,000 values that would give us our audio. In this case, we would need to convert the sine wave equation and calculate that 48,000 times. That gives us 48,000 points that we then connect, and that gives us our sine wave. So the first part of this equation, which is y at t, refers to the output of this equation at time point t. So time point t, if we're just keeping things simple, would start off with 0 out of 48,000, then 1 out of 48,000, then 2 out of 48,000, then 3 out of 48,000, and so on. And then at each one of those time points, we would have some type of calculation. So if we were talking about the world of audio, this would typically be for a sine wave somewhere in the value of 1 and minus 1. So time point 0 out of 48,000 would have some type of value like 0.075. And then you would have one calculation for each one of those time points. So that was one of the things that used to confuse me when I was first starting out. The next part of this, amplitude, just refers to how large or how small we want to make the sine wave. Since we're talking about audio, we want to keep this value between 0 and 1. The next part is the sine function. So many of you probably have seen this on your calculator, and this is a special function that's used to calculate the length of a line as it travels around a circle with radius 1. So a circle with radius 1 is a way that we do trigonomic calculations, and in math this is called the unit circle, a circle with a radius of 1. So you may be asking yourself, well, okay, this line is traveling around a circle. How fast is it traveling? And that's something that we'll come back to a little bit later with frequency. The 2 pi part of this equation is just referring to us doing one full rotation around a circle, representing 2 pi radians. So many of you will probably say 2 pi radians. Well, what is that? So most of you know about degrees, and if I told you to turn 360 degrees, you would turn around in a complete circle, right? So 2 pi radians is just a conversion of degrees into radians, and that's what this is representing. 2 pi is just saying we're doing one full rotation around this circle, and doing calculations for that. So the next part is F, which means frequency. So this is how many rotations that we're trying to do within the time period that's given. So as I was saying before, we're talking about audio with a sample rate of 48,000. So that means 48,000 times in a second. How many rotations around this circle are we trying to do in this 1 second? So many times we use an arbitrary value of 440. This creates a 440 hertz sine wave that we would be able to hear. And so what we're saying is that we want to do 440 turns around this circle, taking measurements using the sine equation. And we want that to happen, giving us 440 sine waves in 1 second, or 48,000 samples. Then T is referring to the current time point that we happen to be in our time series. So as I was saying before, we have 48,000 samples, or 48,000 time points that are happening in 1 second. And this particular T is referring to what is our current time in that time series of 48,000 samples. So that would be maybe 5 over 48,000 or 6 over 48,000. And each time that we calculate this equation, this T variable will go up by 1 over 48,000. So once again, if we're starting with 0 over 48,000, then this equation would calculate for that. Then it would go to 1 over 48,000, 2 over 48,000, and so on until we get our entire series of points that we connect to create our sine wave. The last part of this equation is phi, which is our phase offset. So this is a way that we can take our wave and we can shift the phase of it left or right in the timeline, and we aren't actually going to worry about that for this particular tutorial. All right, so let's take this and convert this over into some pseudocode. So the first part is y at t. So that's the output at time t. And this is just going to change over to our actual audio buffer, output at time s, right? So output is just referring to our audio buffer, and then the s is referring to our place within that audio buffer. Then amplitude is pretty easy. We can just put in an arbitrary value of 0.5, and we just plug that into our equation. Then for the sine and 2 pi aspects of this equation, we have some standard tools that we can use in JUCE or in C++ to calculate those. So I'll show you how to represent those in C++ a little bit later. Then we have frequency. So frequency is pretty easy. We decided on a value of 440 Hertz, which will give us a nice clean sine wave tone that we'll be able to hear. So then we have this aspect T, which is time. To get started, what we're going to do is we're going to introduce sample rate into the discussion. Remember that we're making this calculation of a point in the sine wave 48,000 times per second. So we have the sample rate at 48,000, which means that our time increment, so after each time that we do this calculation, we need to move our time increment 1 over 48,000. So that's where I'm getting this variable time increment from. Okay, so now that we have our variables, what I'm going to do is I want us to take a step back and think more generally about what we're trying to do. So we have this sine wave of 440 Hertz, which means that it's 440 sine waves, and we want to represent that within 48,000 samples of audio, right? Because that's what our sample rate is for 1 second. So we want 440 sine wave oscillations that are happening in 1 second, or 48,000 samples. And the way that we do this, just to review, is that we are creating samples or calculating samples, or what I would call connection points. And what that's going to do, if you look at the diagram, is it's creating values that are going along this line. And as we create those samples or those connection points, what we'll eventually do is we'll draw the line between those connection points, and that's what creates our sine wave. And each one of those time increments is 1 over 48,000 apart, right? Now what we need to do is we need to define where in our sine wave we're currently trying to draw a value, right? Are we at the first place, which would be 0 over 48,000, or are we somewhere in the middle, something like 20 over 48,000, right? And because of that, we need to create another variable that we're calling current time. So that's the current place that we are within that 48,000, so that we're drawing the right sample or the right connection point along our path for this sine wave. So now we're starting to get an idea of the actual structure of our code. And the next thing that we need to do is create a framework or an infrastructure where we can actually do these sine wave calculations and put them into our audio buffer and get those out of our speaker. The way we would do this is using our audio loop, which, as we were saying before, would be in our process function in our sine wave class. So we start the loop, then we do our sine wave equation. So output at S is, once again, our audio buffer. So we're taking the values that we are calculating from the sine wave equation, and we are putting them directly into the output buffer. And we have the amplitude, which is how large or how small we want the sine wave to be. We have the frequency, which is how many sine waves we're trying to generate in 1 second. And then we have this variable current time, which is what part along the time space between 0 and 48,000 are we trying to calculate the value of the sine wave for. So are we trying to calculate at the first index, which is going to be index 0, or 0 over 48,000, or are we somewhere in the middle, which will be something like 24,000 over 48,000? So that is what our current time is. It's just keeping track of where along this time space we currently are. Once we've done the calculation and we've taken the output of that and we've put it into the output buffer, our audio buffer, then what we need to do is we need to increment the current time. So the first time that we do this loop, our current time is going to be 0. Then we add time increment to current time. So that's going to give us a new value of 1 over 48,000. And then we finish the loop, and then we go back to start the loop again. And then the sine wave equation performs again, this time with a current time value of 1 over 48,000. Then current time is going to get incremented again. The new current time is going to be 2 over 48,000. Then the loop is going to repeat, and current time is going to be 3 over 48,000, and so on and so forth. And what that's going to do is create all of these values, and those values are instructing the speakers to move forward and backwards, and that is what is going to create our sine wave. And we have magic. All right, so now that we have that knowledge, let's go ahead and figure out how we actually get this into our sine wave class. First, let's go back to our presentation, and we have these variables that we've created: amplitude, frequency, sample rate, time increment, and current time. Let's go ahead and bring those into our code base as variables. So just a few notes on what I've done here. I've created sample rate and named it current sample rate to differentiate from the argument that I have in void prepare called sample rate. This wouldn't produce an error, but it's just something that's a good practice to make sure that you have your names differentiated. Another thing that I've done is after all of my floats, I've put this F, and this is just to make sure that this number stays as a float rather than becoming a double at some point. Next thing I'm going to do is I'm going to use the current sample rate within my function prepare. So if you remember, prepare is where we get the sample rate from our sound card or from our main audio processor, and we pass it into this sine wave. And what I'm going to do is I'm going to use the current sample rate as the placeholder, so that holds the value to make sure that I'm able to use this elsewhere in my class. If I don't create a class member where I hold this value, then I won't have any other way to access the sample rate. Now, one thing that you'll notice is that we have a warning on sample rate. And if we hover over this, it says narrowing conversion from doubled to float. So we know that current sample rate is a float and that the sample rate that we're passing in is a double. Now, the reason that I created current sample rate as a float is for later on when I'm going to be using that in my calculations. Everything else in the sine wave equation that we're going to make later is a float, and I want current sample rate to also be a float. So what I'm going to do is I'm going to cast sample rate as a float so that we get rid of this warning. So just a reminder that the prepare function is the place that's designed to call whenever the sample rate is changed. And for that reason, this is going to be a place where I'm going to update time increment because that's dependent on the sample rate. So let's go ahead and implement time increment here, which is going to be 1 over the current sample rate. All right, let's dive further in and do some audio processing. And to do this, we're going to need to dig into this JUCE audio buffer object. Now, if you're unfamiliar with the audio buffer object, I would highly advise for you to check out JUCE tutorial 2 in this series. This knowledge is at the very core of audio software development in general, so be sure not to skip over this because this is very important. The first thing that we're going to do is create a for loop where we're going to iterate over each channel of audio that we're going to be processing. So let's do that now. Now we're going to create another for loop inside of this where we iterate over each sample inside the channel of audio. So now we've created a very familiar pattern where we're going through this entire audio buffer and we're going to eventually fill this with the values that we're going to be outputting from our sine wave equation. The next thing that we need is a way that we can actually access the contents of the audio buffer. So in JUCE, you have what are called read pointers and write pointers. Read pointers are a way that we can read what the values are in the audio buffer. So for example, if we were doing some type of audio meter, then we would just need a read pointer because we just need to inspect the contents of each value in our buffer and be able to display that in our graphics. But if we wanted to change the value of what's inside that buffer, then we need what's called a write pointer. And that's what we need in this case, because we're actually changing the contents of what's in the audio buffer because we want to output the values of our sine wave equations. Let's go ahead and create a write pointer now. So this write pointer that we've just created will become the output that we were discussing earlier in our sine wave discussion. So now we have our output and we know what our amplitude is. And now we come to the next two parts of our equation, which are the sine function and 2 pi. Unfortunately, C++ and JUCE have tools for this. So if we go to our browser here, we see that on cppreference.com, we have a sine function that we can use, or in this case, we want sine f since we're dealing with floats. So that's going to be what we're going to use for our sine function. And then in JUCE, they have a constant for 2 pi. So that's what we're going to use to define 2 pi. All right, so now we pretty much have everything that we need to be able to do everything here. So let's go from the left. We're going to do output at S, and this will become output at sample. Then we need amplitude times sine. Remember that we're using the standard library with standard sine f for our sine function. Then we need 2 pi, and this is going to be, once again, represented by our JUCE constant 2 pi. The way you type this out is a little bit tricky. It's JUCE, math constants, then we need to specify what type it is. In this case, it's type float, then colon, colon, then 2 pi. The next part is times frequency times current time. Now we just need our next line of code, which is current time equals current time plus time increment. Okay, so now we've implemented our sine wave equation, and the next step will be to try and create one of these sine waves within our main plugin processor and see what happens. One thing I will preview for you though is that this is not quite right yet, but it's better if I show you what happens and then show you how to correct it. So let's go to our plugin processor.h. And what we're going to do is we're going to include our sine wave.h. So we can create our object. Now let's scroll down to private and let's create a sine wave. Now let's go to our plugin processor.cpp. Down to prepare to play. And now we will do sine wave.prepare. Then let's go down to our process block, go down to the very bottom, and then we will do sine wave.process. And then this takes in our buffer object. Now, you want to turn down your headphones to make sure that you don't damage your ears, but I'm going to go ahead and hit compile on this and show you the noise that you're going to get. The thing is that it's not going to be a sine wave, and I'm going to tell you why. Well, that didn't sound anything like a sine wave. So this is one of the most common mistakes that gets made in audio processing, and I'm going to show you why. Let's go back to our sine wave class. Now, what I'm going to do first is I'm going to change some of this code around so we can log some values, and then I can show you from the values where the mistake is being made. So I will be right back. All right, so what I've done is I've hacked together some values to give us an idea of what's going on with the audio, but don't pay attention too much to the code that I've added there. Before we step into the console values, what I wanted to do was give you a general idea of what's happening with the audio. So here we have our audio buffer object, and what we're doing with this nested for loop is that we're going through each channel of audio. So in this case, we have two channels of audio, our left speaker and our right speaker. And then in each channel of audio, we're going through our sample buffer for each channel. And in this case, we have 512 samples in our sample buffer. So it will go channel 0, then fill up those 512 samples. Then it'll go channel 1 and fill up those 512 samples. So in here, we have our sine wave equation. And the problem that we're having is with current time. Because what's happening is that in this first iteration, so let's say that we're going through this loop the first time around, we're in channel 0, starts with sample 0, and then it goes up to 511, which gives you 512 values. And then you have your time increment. Remember, time increment starts at 0, which is the time that we initialized it to. And then what it's going to do is it's going to go up by 1 over sample rate for every iteration through this for loop. So that brings us down to these numbers here that I have in the console. So what happens is that when at the end of each iteration of the for loop, we get an addition of 1 over 48,000, which is our sample rate of the sample. And this is going to happen all the way down to 512. So let's go there. So as you can see, we end with 512 over 48,000, and that'll be our current time. Now the problem starts when we go to our second channel, which is channel 1, because we would like for this to start on the other speaker with 0 over 48,000, but we can see that it's not. It's actually starting with 513 over 48,000, which doesn't give us a signal of 0, but it gives us a signal that is part of a sine wave, but not starting off at the value of 0 like we would want it to. But then the problem gets even greater, because let's look at what happens when we go back to channel 0 again. So this is going to fill up to 1024. And then what happens is that we go back to channel 0 again. And where we left off with channel 0 when we finished the first time was at value 512. So we would like for this value to be value 513 over 48,000, but we see that it's not. It's value 1025 over 48,000. So what's happening is that it's drawing part of the sine wave from 0 to 512. And then rather than going with 513 up to 1024, it's starting with number 1025. So it's drawing a different part of the sine wave. So what's happening is that each speaker is drawing part of the sine wave, and it's going back and forth. Now, this is a problem that happens all the time in audio. And generally speaking, what the rule of thumb is that you want to create a DSP process for each channel of audio that you're processing. So as you can see, we have 2 channels of audio that we're processing, but we have only one DSP process that's happening. There's a very simple way that we could correct this problem, which is that we could take current time and we can make this where we have a current time for each channel of audio that we're processing. That's probably the easiest way for us to do this. There's another way that we could do this as well, which would be that we would take all of the channel information out of this process function, and we would move all of the channel processing into our main plugin processor, and then we would create two sine wave processes or two sine wave objects, one for each channel. Okay, so I'm going to show you how to do both of those, but for now, I'm just going to show you the most simple one, which is to create a current time for each channel of audio that we're processing. The first thing that we're going to do is we're going to make current time from a float into a stood vector of floats. And we're going to have a current time for each channel of audio that we're going to process. Now what I'm going to do is add another parameter to our prepare method where we're going to take in the number of channels that we want to process for our audio. Now let's add the number channels parameter to our prepare method in our C++ file, and then use that to resize the size of our vector current time. Here I'm creating this new parameter num channels and using that to resize the size of our vector current time and initialize each one of those indexes with a value of 0.0. Now we need to update current time in our process loop since this is a vector rather than a float. The size of current time should be equal to the number of channels that we're getting from our buffer. So let's go ahead and update that. Here we're making an assumption that the number of indices in current time is equal to the number of channels. Let's go ahead and add a check to make sure that this is the case. And if it's not the case, then what we can do is make sure that no other audio processing happens. This check ensures that the process loop will not complete unless this prepare method has been called first, where we resize current time to the number of channels of audio that we're processing. Now what we can do is go back to our main plugin processor because we need to update prepare because we've added this extra parameter number of channels. Here we can use the JUCE function get total number output channels to get the number of output channels from our buffer. And now we should finally have our sine wave working properly. Let's go ahead and build this. So there we go. Congratulations, you've now created your first audio plugin. All right, let's talk about a couple extra things that we can do here to make our audio processing class for our sine wave in line with what you would typically see for an audio processing class. So we have these two parameters, amplitude and frequency. So if we wanted to make this into a real audio processing class, one thing that we would like to do is be able to give our users access to these parameters using getters and setters. So what we'll do is create two methods for each one of these. One of these will get the amplitude back so that the developer could see what the amplitude is currently. And another one is where we could give the developer access to set the amplitude. And we're going to do the same thing for frequency. So let's go ahead and do that now. So here I've created two functions, get amplitude and get frequency, that will return what the value of amplitude and frequency are at the current time. Now we're getting a warning here that these functions can be marked as no discard. So the keyword no discard is a way that we can let developers know that the return value that they're going to get from this function is not going to be void. There's going to be some type of value. In this case, it's a float. Then we have const. This is letting us know that this function is not trying to change the class members' amplitude and frequency. It's just reading what those values currently are. Now let's create some setter functions for amplitude and frequency where we can update new values for those class members. So now we've created some setters. Notice that I've marked these values as const. So this ensures that new amplitude or new frequency is not going to be changed anytime within this function. We can also do this for our prepare function, where the sample rate and the number of channels cannot be changed before we pass it on to one of our class members. Now we have a pretty clean looking audio processing class, and this is a typical type of class that you would see for any type of DSP process. You're going to have some type of prepare or set sample rate or prepare to play function that allows you to pass on the sample rate, potentially the buffer size and the number of channels that you're processing. You're going to have some type of process or get next audio block type of function where you're going to do your real-time audio processing. And then you'll probably have some getters and setters that are going to allow you to have access to these different class members and be able to update those. All right, so as promised, I said that I would show you another way to write this class. And this is a way that you'll typically see in C++ if they're using a framework that's outside of JUCE. So the way that I'm going to write this class is just using raw C++ without any JUCE tools. And this is a little bit more for intermediate developers, but feel free to follow along and tell me what you think. All right, here we are in this new class that I've written called Sine Wave Channel. And one of the things that we need to do is make sure that we have access to the numbers header that's a standard C++ header. In order to do that, we need to be on C++ 20. The way you would do this in your CMake list is to make sure that the C++ standard that we have is set to 20. Taking a look at the class itself, the class is actually very similar to what we've written before. There are a couple notable differences, however. Starting at the top, we'll see that prepare used to have the number of channels that we're looking to process, but that is no longer the case because we don't need that information anymore because we're taking that channel dependency and we're moving it out of this class. Also, we'll see that the process method was taking in a JUCE audio buffer object. But now what we can do is we can make that a float pointer instead of a JUCE audio buffer and the number of samples that we're looking to process. The reason that we're able to do this is if we go back to our sine wave class that we've written before, we'll see that the buffer get right pointer function returns a float pointer. So that's the way that we're able to remove that JUCE dependency and give us a standard C++ parameter of a float pointer. The other thing that we've done is we've taken current time and we had that as a vector, and now I've returned it to a float rather than a vector because this is going to be responsible for just its own audio process, not for managing all of the channels that we're trying to process. Now let's go over to the implementation. This is pretty much the way that we had it before. So we're taking the current sample rate, we're casting it as a float, and then we're doing our time increment, same thing as we were doing before. Moving on to our process method, we can see that this is very simplified from what we used to have before because once again, we're taking the channel information, we're pulling that out and just making a DSP process that we'll later do for each channel of audio in our main plugin processor. So here we are just taking in the pointer to our output, to our buffer, and the number of samples that we're trying to process. Now we're using number of samples as the number of samples that we're iterating through that we'll get from our buffer get number samples method. And then we're taking this, and once again, this is largely the same, except the one difference is that I'm now using this stud numbers pi v, which is a new tool from the numbers header that we have in C++ 20. So C++ 20 now has some constants that we can use for numbers like pi. So I've replaced the JUCE pi with this, and I need to make sure that I multiply that by 2. Now let's go over to our plugin processor header file. And what I've done is I've included the sine wave channel header. And now instead of creating one sine wave, what I've done is I've created a vector of sine wave objects. This is because we need to have a sine wave object for each channel of audio. Now going to our plugin processor, if we go up to prepare to play, we can see that I've created a number of sine wave objects that are equal to our total number of output channels. And then for each one of those sine wave objects, I've called wave.prepare. Going down to the process block, what we see is that once again, I've taken all of the channel processing and I've moved that out of the class and into this main audio processor. And then what I've done is I've created a right pointer, and then I have just called sine wave.process for each channel of audio, and then given it the output and the number of samples. So if you're focused on writing some more dependency-free type of code that just uses raw C++, then using this type of strategy for writing your sine wave or your audio class may be the way for you. This is also a way that will help you understand what types of things that you need to do if you see a class like this, that's a DSP class that is not bringing in any information about the channels that you're processing. So in that case, what you're going to need to do is create a vector of DSP processes for each one of your channels. And then at each step of the way, in prepare to play, and then in your process block, you need to be able to step through each one of those DSP processes and do the process by channel individually. All right, and that's our tutorial for today. I know that we went through a lot, and if you found that helpful, be sure to give us a like and subscribe. I really hope that this helps you in your audio programming journeys. So until then, I'll see you next time. Happy coding.